Welcome to Lecture 22. This lecture, we're going to go through a number of the formal aspects related to scattering in 3 dimensions. We're going to be focusing on scattering off of point objects or point potentials that have spherical symmetry. And the way that we described this was we have an incident wave that comes in. When it hits that scattering center, it creates spherical waves that come out. And because in a spherical system, I can't transmit through r equals 0, everything that comes out is a reflected wave. So in essence, all of the behavior of scattering in 3 dimensions off of a spherical point source involves working out the phase for the reflection coefficient, which is often called the scattering phase shift. Now, if you remember, we derived this Lippmann-Schwinger equation, which said that the ket psi k was equal to the ket psi 0k plus g plus of e v psi k. That is an equation for psi k. In this case, E is the energy of the free particle with momentum k, so it's just given by h bar squared k squared over 2m. And the g0 plus of E was given by E minus h0 hat, the operator, plus I delta. Okay? We also work through evaluating this in the coordinate representation, where we look at matrix elements with regards to coordinate bras and kets. And if we evaluate in the coordinate representation that Green's function g0 plus has matrix elements for a given position vector r and a second position vector r prime, and the matrix elements become minus m over 2 pi h bar squared e to the I k modulus of r minus r prime over modulus of r minus r prime. Now, I've not done the derivation of this for you. It's very closely related to the derivation that we already did in 1 dimension. It does require using contour integrals, and I'm just not going to go through those details. It's a little bit of a technical detail. I don't think it's particularly enlightening, so I'm not going to go through those details. But when we write this equation now in that coordinate representation, what we have is psi k of r is equal to psi 0k of r minus 1 over 4 pi, the integral d cubed r prime e to the I k modulus r minus r prime over modulus r minus r prime times 2m over h bar squared of v of r prime psi k of r prime. And that is an integral equation for psi k. We start off with a psi 0k. We input the potential v, and we have to find the psi k of r that solves that equation. And as we mentioned before, a typical way in which you would solve this is by iteration. So you would take the psi k on the right-hand side, you would replace it with a psi 0k, and then that would give you psi k is equal, on the left-hand side, is equal to psi 0k plus this integral that involves a psi 0k. You can then take that and substitute it into the right-hand side of the equation again, and so forth, and you'll ultimately generate a series of these different terms. And that is one way in which you could imagine solving this, and potentially even just doing this numerically if I gave you what a v of r was. All right, we're going to start by focusing on the behavior for large r. This is not because this is just a exercise because we think things might be easy there. There's a physical reason for this. We typically are looking at scattering very far from the scattering center. If my scattering center is an atom, then in order for me to see the scattering at all, the signal must be amplified onto a screen that is far away from the scattering centers so that I can actually see and pick out where the different scattering particles will hit the screen. So this is the really physical regime. We're always interested in scattering in the large R limit. Now, the types of problems that you can actually solve in non-relativistic quantum mechanics involve v of r's that are non-zero only in a region where r prime is small, and they decay sufficiently fast for large r prime. Now, unfortunately, it turns out that the Coulomb interaction, which is the most important scattering problem, does not fall into this category. That is a problem that requires more work to try to get out what happens with the Coulomb scattering. And of course, the Coulomb scattering problem is actually the Rutherford scattering problem, which is a very famous problem and a very important one in quantum mechanics. But we're not going to actually work on that problem here because it is a little bit too complicated and a little bit too technical to go through those details. Okay, so we're looking at some other scattering potential that decays faster than 1 over r. as r goes to infinity. So what we want to do is we want to expand this modulus r minus r prime because that enters into the formula for the Green's function. We simply multiply and divide by an r, and then notice that r over r, that's a unit vector. Or if you like, we actually just expand that modulus out, and we'll get the r out in front, and then we'll get a square root of r squared over r squared, which is 1, minus 2 r dot r prime over r squared, plus r prime squared over r squared. Now we can further expand this under the assumption that r prime is small relative to r, because r is big and r prime is limited to lie close to where the potential is large. We will get r times 1 minus r dot r prime over r squared. That's the term that's linear in r prime. The 2 is divided by a 1/2 because I'm raising this to the 1/2 power. Then I will also get a second term that will be a plus r prime squared over r squared times a 1/2. That's the linear Taylor series expansion of that r prime squared term. And then I get a second term, which is the quadratic expansion of the middle term. That will have a factor of 1/2 times minus 1/2 times 1/2. And that's a total of minus 1/8. The 2 is squared. That gives me 4. So I get a net of minus 1/2. And I'll have an r dot r prime squared over r to the 4th. Now, as you recognize, and I've already mentioned this, r vector over r number, the radius, is a unit vector. We'll call that unit vector ER. It's a unit vector in the r direction. Then I can rewrite this as r, the scalar quantity r, minus ER dot r prime. Notice that there are no vectors. It's all scalars on the right-hand side because the norm of a vector is always a scalar. All right. Now we can now take this and we can expand 1 over r minus r prime. We're going to write that as 1 over r times 1 over 1 minus ER dot ER prime r prime over r. Remember, r prime over r is going to be small, so we can expand that as a geometric series. We're only going to take the lowest order term. That's simply going to change the minus sign on the bottom to a plus sign on the top. So we'll get 1 over r times 1 plus ER dot ER prime times r prime over r. And we can rewrite that, if we wish, as 1 over r plus ER dot ER prime r prime over r squared. Okay. Now, of course, there are higher order terms that I have neglected in this, but this is accurate to order r prime, linear order in r prime. We now are going to multiply this by k. We're going to get k times r minus r prime. We're going to get kr times 1 minus er dot er prime, r prime over r, plus higher order. We're now going to take the opportunity to define a second scattering wave vector that we're going to call k prime. It's simply defined to be er dot k. So k prime is a vector that is pointing in the r direction. Since the r direction is all of space, because I'm controlling what direction I'm evaluating my scattering wave function in, that corresponds to any particular scattering wave vector. We're thinking of this as elastic scattering, so the k prime has the same magnitude as the k. All right, using that definition then, we can substitute into what we have already worked out, and we find k times r minus r prime is given by kr minus k prime dot r prime. All right, now we can plug that into the integral formula that we had. We had psi k of r is equal to psi 0 k of r minus 1 over 4 pi integral d cubed r. That exponential term that we had becomes e to the I kr minus I k prime dot r prime over r. And then the 1 over r minus r prime in the denominator becomes 1 plus er dot er prime, r prime over r. Whole thing times 2m over h bar squared v of r prime, psi k of r prime. Now we know that our unperturbed scattering wave is a plane wave. So psi 0 k of r is 1 over 2 pi to the 3/2 e to the I k dot r. And that means we can plug in for the psi k of r. We'll get 1 over 2 pi to the 3/2 e to the I k dot r plus e to the I k r over r. Note k dot r and k r are not the same thing. And we're going to call the thing that second term multiplies f of k prime k plus order r prime over r. Now we have to work out what the f of k prime k is. You can read that off from the integral. The f of k prime k is going to just be minus 2 pi squared integral d cubed r psi 0 k prime star of r prime. You notice that e to the minus I k prime dot r prime, that's psi 0 k prime star of r prime. We have the 2m over h bar squared. We have the v of r prime. We have the psi k of r prime as well. Okay, so that's just reading off of the formula that we already had. We are dropping the terms that are linear in r prime and higher order now. We initially were just dropping the terms of order r prime squared. Now we're even dropping the terms of order r prime. All right, we can rewrite that scattering amplitude f of k prime k in terms of the Dirac-Braket notation. We get minus 4 pi squared m over h bar squared psi 0 k prime v hat psi k. All right, the scattering amplitude has units of length. We can tell that by going back to the definition here. You see the term e to the I k dot r. That has no length in front of it, but we wrote the second term as e to the I k r over r. That's because the spherical wave will decay like a 1 over r. And then that f of k prime k must have dimensions of r in order for these two terms to have the same dimensions. Okay? Now, the way that you should picture this is we have some k that is incident. That's fixed by the experiment and how we're working this out. And then we'll have some outgoing k prime at some angle theta relative to the axis of the initial k's that are coming in. And you can think of f of k prime k as the amplitude for an outgoing spherical wave in the direction to be coming out in the direction of k prime. Now, it's going to turn out in all of our scattering, these results are independent of a phi angle that you can take, which would be the angle about the axis given by the k, and the total dependence is going to be depending entirely on the theta. All right, the square of this is the probability to observe the particle with momentum h bar k prime after scattering, the incident momentum being h bar k. And we define the differential cross-section to be d sigma d omega k prime. That's the spherical directions corresponding to the scattered wave vector k prime. It's the probability per time per solid angle of scattering in the k prime direction divided by the probability per unit time per unit area of incident flux of particles. And then sigma, which is called the cross-section, is the integral d omega of d sigma d omega, and that cross-section has units of area. One way you might want to think about the cross-section is if we had a classical sphere of a particular size and I threw like BBs at it, then I would get a shadow effect where no BBs hit because they were scattered by the sphere, and the area of that shadow would be the cross-sectional area of the sphere. And that's in essence where this name cross-section comes from. It's kind of like you're looking at the cross-sectional scattering area of the thing that you are scattering off of. Now, the scattering cross-section is a function of that incident momentum, h bar k, or a function of the incident energy, E, and the direction of the incident path, but it does not depend on whatever frame of reference you're going to be using. All right, Gottfried, in the readings for this, Gottfried discusses how we can show that the differential scattering cross-section d sigma d omega k prime is given by the modulus squared of f of k prime k. I'm not going to go through that derivation for you here, but you need to understand that that is the relationship between the differential scattering cross-section and the scattering amplitude. That's a very important relation. The derivation is a little bit technical, and I point you to the reading by Gottfried that is going to go through that derivation for you. Now, these results are often summarized in terms of something that we call a T-matrix. The T-matrix is going to be defined in the following way. We start from our Lippmann-Schwinger equation. Psi k is psi 0 k plus g0 plus of e v hat psi k. We can then solve that as we know we can. Psi k is 1 minus g0 plus of e v inverse psi 0 of k, and then we replace that term that we previously were expanding as a geometric series with an operator that we just call capital omega plus of e. Capital omega plus of e, that operator is called the molar wave matrix. And then in terms of that molar wave matrix, f of k prime k, because we have a simple expression for that, in terms of the initial and the full scattering states as minus 4 pi squared m over h bar squared psi 0 k prime v hat psi k, we can substitute in for that psi k in terms of the omega plus psi 0 k, and we'll get minus 4 pi squared m over h bar squared psi 0 k prime v hat omega plus of e psi 0 k. And, you know, this is just notation here. There's nothing fancy, complicated, or anything like that going on here. And then what we do is we define v times omega as the T matrix, and we'll call that T hat of E. Again, just a definition, all right? That means that f of k prime k is minus 4 pi squared m over h bar squared psi 0 k prime T hat of E psi 0 k. So it's a it's an off-diagonal matrix element, or just matrix element of T of E in the initial plane wave basis. So we call that minus 4 pi squared m over h bar squared T of k prime k of E. Now this operator T of E satisfies a couple of different operator equations. It satisfies T is equal to V, 1 minus G0 plus V hat inverse. That's essentially just plugging in the definition of the molar matrix because T was equal to V omega. We now can multiply both sides on the right by 1 minus G0 plus V, and we'll get T minus T G0 plus V is equal to V. And then I can just rearrange that to T equals V plus T G0 plus V hat. Another way of doing it is we just expand that geometric series. We'll get T is equal to V plus VG0 plus V plus VG0 plus VG0 plus V, and so forth. And that is this expansion of 1 minus VG0 plus inverse times V. I'm now refactoring that. I'm now pulling out the factor of V on the right as opposed to on the left. You see that that is going to be the same thing, but now it's a 1 minus VG0 plus as opposed to a 1 minus G0 plus V. Okay, so be careful. You see what we've done with that geometric series and how we've factored it. And then I get the equation when I multiply by 1 minus VG0 plus from the left, I'll get 1 minus VG0 plus T equals V. And then if I just multiply that out and move the VG0 plus T to the right-hand side, we'll get T is equal to V plus VG0 plus T. So these are two equations that must both be satisfied. And it tells you that there's something special about this T matrix because you can write this expression with the T matrix in that second term on the right-hand side, on the left-hand side, or on the right-hand side. All right. Now, because G0 plus minus is 1 over E minus H0 plus or minus I delta, that's our definition of what G0 plus minus is, G0 plus Hermitian conjugate of E is equal to G0 minus of E. You get that because E is real and H0 is Hermitian. So if I take the Hermitian conjugate of G0 plus, all I will do is change the sign of the I in the denominator. So when we take the Hermitian conjugate of those two equations that we just derived, we'll find T dagger equals V T dagger G0 minus V. And it also equals V plus VG0 minus T dagger. Now we have to go back and recall the Dirac delta function identity where he said that 1 over x plus or minus I delta is equal to the principal value of x minus plus I pi delta of x. I'm not sure whether you guys have seen principal values before. Effectively, what principal value means that when I'm evaluating 1 over x, when it appears in an integral, I have to evaluate it symmetrically on both sides of the x, and I don't evaluate it at x equals 0. So it really has a definition primarily in the context of an integral. You also can evaluate this for a non-zero but finite delta, and by taking the real part of 1 over x plus or minus I delta And you will see that it has a symmetric form exactly like I said, because it will be exactly equal to 0 at x equals 0 as long as the delta is non-zero. So when we take the limit as delta goes to 0, that is essentially what this principal value is. So it has no actual singularity in it, although it gets very, very large as we approach 0. All right? And then the imaginary part will be a very sharply peaked function that will have a width that goes like delta. So if I take, but the integral under that is equal to pi, because you can just integrate that as an arctangent, and you will find then that that imaginary part is going like a delta function, and then you just have to work out the signs. You find it's minus plus I pi delta of x. Now this is a very important identity. I encourage you to be sure that you know this identity. If you need some more work on it, what I just explained is not sufficient for you to understand this identity, then I do encourage you to bring it up during our class time, and I'll work on explaining it further for you. All right, we're going to now calculate t minus t dagger, because both the t and the t dagger equations each had v's in them, and I'm subtracting. The v terms are going to cancel. We'll get a v g0 plus t minus a t dagger g0 minus v. You see I've carefully chosen the different forms that I'm going to be using for the t dagger equation and for the t equation in order to get this to work, because there are 4 different choices I could have made for those equations in the way that I determined that second term on the right-hand side, and I chose it in this particular way. And then what I'm going to do is I'm replacing the v. So now if I look at that top equation, t dagger equals v plus t dagger g0 minus v, or v equals v plus v g0 minus t dagger, I'm going to be replacing the v by a t dagger minus t dagger g0 minus v. So I'm going to be using the first form of that equation. I'm going to do a similar thing by replacing the v in the second term using the t equation. And there I'm going to be using v equals t minus vg0 plus t. And what is nice about this is the complicated term, the t dagger g0 minus vg0 plus t, that cancels between both terms. And we're just left with a more simplified expression, which is t dagger g0 plus minus g0 minus t, because I can factor out a t dagger to the left and a t to the right. Okay? Now, g0 plus minus g0 minus, that is equal to the principal value of 1 over e minus h0 minus I pi delta of e minus h0 minus the principal value of e minus h0 minus I pi delta of e minus h0. So that is a simple form. It's just equal to minus 2 I pi delta of e minus h0. I can plug that in and we get this remarkable operator identity. T minus t dagger is equal to minus 2 pi I t dagger delta of e minus h0 t. I cannot pull that h0 out because it doesn't necessarily commute with the t matrix. This is called the generalized optical theorem. We can now take this operator identity and look at matrix elements of it. We're going to multiply by a psi 0 k prime from the left using a bra and a psi 0 k from the right using a ket. We're going to introduce a complete set of states on both sides of the delta function using energy states, or if you like, momentum states, which are also energy eigenstates. And what we find is tk prime k of e minus tkk prime star of e is equal to minus 2 I pi integral d cubed k double prime integral d cubed k triple prime tk double prime k prime of e star matrix element k double prime delta of e minus h0 k triple prime tk triple prime k of e. Now, we can look at that matrix element with the delta function. Because I'm in an eigenbasis of h0, I can just replace the h0, substitute in for the h0 with its eigenvalue, which is h bar squared k double prime squared over 2m, or I could have picked k triple prime because I get the overlap of k double prime with k triple prime, which is just a delta function, a delta cubed of k double prime minus k triple prime, because the momentum wave functions are perpendicular with a delta function normalization. So because we get this delta function over k, I can do one of those k integrals, and we're going to integrate over the k triple prime. Furthermore, the integral d cubed k double prime of a delta function with this energy difference, I'm going to go to spherical coordinates and write that as an integral from 0 to infinity dk double prime k double prime squared, integral d omega k double prime, those are the angular parts, delta function of e minus h bar squared k double prime squared over 2m. The radial integral can be done exactly. And you have to just remember that when I do a delta function where I have a function inside the delta function, I have to divide by the derivative of the delta function, which means I have to divide by an h bar squared k over 2m. The k is going to be replaced by the square root of 2m e over h bar squared, or square root of 2m e over h bar. So when all the dust settles, you put that all together, you're going to get an m over h bar squared, square root of 2m e over h bar, integral over the angle coordinates, or after a simplification, mk over h bar squared, integral d omega k double prime. So we're going to get rid of nearly all of the integrals, and we find that tk prime k of e minus tk k prime star of e is going to equal minus 2I pi mk over h bar squared, integral over the angles for k double prime, t k double prime k prime of e star, tk double prime k of e. Now we're going to multiply by minus 4 pi squared m over h bar squared. That converts the t matrix into the f, the scattering amplitudes. We're going to get f of k prime k minus f star of kk prime is equal to ik over 2 pi integral d omega k double prime, f of k double prime k, f star of k double prime k prime. Okay, this result is called the generalized optical theorem for the scattering amplitude. The way that we use this generalized optical theorem is to look at forward scattering. So that's the case where k prime is in the same direction as k. In essence, these are the particles that are not scattered. It is the case that corresponds to theta equals 0. Then if you look at the left-hand side of the generalized optical theorem, because k prime equals k, I'm just getting twice the imaginary part of f of kk. There's an I there, but I'm going to cancel the I from both sides. And then on the right-hand side, I'll be left with a k over 2 pi integral dk double prime of the modulus of f of k double prime k, because when I set k prime equals k, you see that becomes the modulus of f of k double prime k squared. But remember, Gottfried told us that the modulus of f of k double prime k squared is just d sigma of k d omega k double prime. When I integrate that over d omega k double prime, I'll get sigma of k. So what we find is that sigma of k can be expressed as 4 pi over k, the imaginary part of f of k. That's a remarkable identity, and it tells us that once we have found the scattering amplitude, we don't have to take the modulus squared and integrate it. I can immediately tell you what the total scattering cross-section is. It's only if I want to get the differential scattering cross-section that I have to work and calculate the modulus of an f of kk prime. Okay, so that's a remarkable result. That's called the generalized optical theorem for the scattering amplitude. And it's something that comes in very handy if you're trying to do calculations of what the total scattering cross-section would be. All right, the last bit we're going to go over is the Born series. That T matrix is 1 minus V G0 plus inverse times V. From that, we can get f of k prime k by multiplying by a bra and a ket and multiplying by this 4 pi squared over h bar squared. So we get minus 4 pi squared m over h bar squared. Psi 0 k prime, bra, 1 minus v hat g0 plus of e, whole thing inverse, times v, psi 0 k. And we're going to expand that in a power series, a sum from n equals 1 to infinity of an fn of k prime k, where n is counting the powers of v. Each of those different f's with a subscript is called the nth Born approximation. Technically speaking, the nth Born approximation is the sum of all of those terms up to some big capital N. And as I had mentioned before, the most important approximation is the first Born approximation, where we just use one term there. So the first Born scattering amplitude, f1 of k prime k, is minus 4 pi squared m over h bar squared. Bra psi 0 k prime, v hat, ket psi 0 k. So I just have to evaluate the matrix elements of the potential in the plane wave basis. Well, that turns out to be the Fourier transform, as you can immediately see. When I plug in what psi 0 k is in position space. So you can just imagine I'm plugging in a complete set of states, multiplying, in between, on either side of the v, doesn't matter which side, and I'll get a 1 over 2 pi cubed integral d cubed r e to the minus I k prime minus k dot r v of r. After absorbing those constants, you see that that is going to be the Fourier transform of v. I can see that I've actually dropped a couple of constants there because of the mass and the h bar squareds. They're not going to immediately cancel from this. But it is proportional to that Fourier transform, which we're going to denote v tilde of k prime minus k. All right, so what we're saying is that psi 0 k prime v psi 0 k is given by v tilde of k prime minus k over 2 pi cubed. And that is incorporating all of the particular constants in the way that we want to incorporate them for the definition of what we're calling v tilde. So using that definition, then we can calculate the second born, f2 of k prime k. That's given by minus m over 2 pi h bar squared v tilde of k prime minus k plus 2 pi cubed integral d cubed k double prime of psi 0 k prime v psi 0 k double prime times psi 0 k double prime g0 plus of e v psi 0 k. But psi 0 k double prime g0 plus of e, we can just evaluate that because when the Hamiltonian acts on that function, it's an eigenfunction of that state. So I just replace h0 by its eigenvalue. So I get 1 over e minus h bar squared k double prime squared over 2m plus I delta. And we find that the second born scattering amplitude is minus m over 2 pi h bar squared v tilde of k prime minus k. So the v tilde of k prime minus k, that's the first born approximation, plus this integral d cubed k double prime over 2 pi cubed v tilde of k prime minus k double prime v tilde of k double prime minus k e minus h bar squared k double prime squared over 2m plus I delta. Now notice this integral over k double prime is over all possible k double primes. So those h bar squared k double prime squared over 2m does not need to equal E. E is the energy of the incident electrons. And so this is bringing in some potentially inelastic scattering terms. And the technical term that we use for this scattering is we call it off-shell scattering because some parts of that integrand contribute when the h bar squared k double prime squared over 2m does not equal E, which is the condition for elastic scattering. And you can think of this occurring because for a short time, the energy of the quantum particle is not known so precisely and so forth. But of course, if you look at that principal value, if you look at that term, the E over E minus h bar squared k double prime squared over 2m plus I delta, that term is of course very sharply peaked when the k double prime is such that h bar squared k double prime squared over 2m is approximately equal to E. So you do have a dominant contribution from the terms that are on shell, but you also pick up or start picking up contributions from terms that are off shell. Now, if you ever go further and study quantum field theory, this becomes a big deal in looking at particle scattering, which is a bit more complicated than potential scattering, which is what we're looking at here, but it still has the same concept of on-shell or elastic scattering versus off-shell scattering. All right, that brings us now to the end of Lecture 22. In Lecture 23, we're going to be continuing with the scattering theme.